Recently, Triband released a demo of an upcoming game that they're porting from Apple Arcade to PC. They released one demo in the past. It was a collection of a few levels um, on like a small overworld map. But this time, they just released a new demo with 33 levels and even some custom ones. And I challenged myself, and I had a few thoughts. If I could find the mass of the car from what the car. So I put a poll out on the Triband Discord server, and overwhelmingly, almost everyone said that I should make this video. So here we are. I'm going to try to calculate what is the mass of the car from the What the Car demo. So the first order of business is figuring out which level will be the best one to use to calculate the mass, and I think this one with the chairs is the perfect option because we're given real life objects that we can hopefully use to figure out the size of the world, and from there calculate speed. So launching out of this cannon, the initial speed is not 0, which is a bit annoying, but we can hopefully work with it. You know what's even more annoying? The fact that there's friction. Have you ever wondered what a physics student's worst nightmare is? Well, it's when friction is non-negligible. I'm going to assume that it's more so friction than air resistance simply because there doesn't appear to be any air here, and we're moving at such a speed that it really wouldn't be that much of an issue. And also because it's easier. So that's step 1. On to step 2, which is figuring out how on earth we're going to find the mass of this car. So my first thought would be to use the law of momentum conservation, which states that momentum is equal to mass times velocity, and that momentum is conserved in collisions. So I was thinking that maybe I could just, collide into one of these chairs or desks and measure the velocities before and after and use that to calculate the mass. But since nothing is ever that simple, we also have friction, which led me to maybe try using the law of energy conservation instead, which states that energy cannot be created nor destroyed, only transferred. So maybe I could collide into one of these chairs or something and calculate the speeds of the objects before and after the collisions, then subtract friction here because I am slowing down and that's energy leaving the system, and use that to calculate the mass of the car. So let's try that. First order of business is calculating friction. We can denote friction by using the friction coefficient, or this fancy Greek letter called mu, which is not at all how the Greeks pronounce it.
Me, not mu. Me.
And that has always bugged me, but in physics class, you don't learn Greek, so whatever. So now how do you put friction in the equation? It's simple. You can just put the friction coefficient in this equation that says that friction force is equal to the friction coefficient times the normal force. What's the normal force? Well, it's simple. It's just mass times the gravitational constant g. What's g? Well, that's a damn good question. And hey, it looks there's mass, which is the variable we're trying to solve here, that's well. So then I thought, well, why not use the time it took to stop the thing into consideration? That's got to be of use somehow, right? Well, by golly gee, yes sir, that is a thing you can do. So in order to solve for the frictional force of the ground to the car, we need to consider the fact that this car is not just a car, but is a car on 4 chairs, which have wheels. And you know what that means? Rotational motion. Hooray. Okay, so to proceed, we first need to calculate the time it takes for this car to slow down from its initial speed to when it stops. I will consider initial speed as the speed of the car when I take control, which is around the time I land on the ground, which is around 50 seconds. Next, I'll take that time and plug it into this equation here, which relates angular velocity to angular acceleration and time, which is, what is angular velocity? Good question. It's how fast something turns in radians per second. In order to find that, we need to consider how big the wheels of these chairs are. They look to be pretty basic office chairs, and judging by the wheel size of the chair I'm currently sitting in, they are conveniently exactly 2 inches long, which makes things really easy. The office chair's wheels have a radius of 1 inch, which is equivalent to 2.54 centimeters or 0.0254 meters. But how fast is the car moving initially? Well, we can relate the car's velocity to the other stuff in the office room, such as this desk here. This desk looks to be this desk I found online, which conveniently states that the length is 39 inches, or around 99.06 centimeters. It looks like the car passes the length of the desk in 0.44 seconds, so 99.06 centimeters per 0.44 seconds is equivalent to 225.136 centimeters per second, or 2.2516 meters per second. Alright, so now that we have velocity and radius, we can plug it into our equation and we get that the angular velocity is around 88.63 radians per second. Wow, okay. So now that we have the angular velocity, let's plug that into our equation to determine the angular acceleration. We take the angular velocity and divide it by the time it takes to stop in the initial angular velocity, which is around 52.56 seconds, and so we get an angular acceleration of around negative 1.686 radians per second. God bless. Okay, let's do a recap. I want to find the mass of this car, and to do that, we can use the law of the conservation of energy, but that requires knowing the friction force, and we can't solve it for it using mu and mass because we don't have those things. So instead we can use torque to find it, but to find torque we need acceleration, and to find acceleration we can use distance over time, but we don't have distance, so by solving for the average angular deceleration of the wheels of the chairs, we needed the radius of the wheels and the time it took to travel a certain distance. Okay, let's continue. So to find the friction force, we can redefine torque as the force times the distance between the place where you applied the force and the hinge times the sine of the angle at which you exert the force, aka the friction force times the radius of the wheel. The floor isn't really exerting a force in an angle, so we can call it a right angle, and sine of 90 is 1. So since torque is also equal to the moment of inertia times the angular acceleration, we can move around some variables to get that the friction force is equal to the moment of inertia times the angular acceleration divided by the radius of the wheel. We have radius and angular acceleration, so all we need is the moment of inertia. The wheel's moment of inertia can be calculated by the mass of the wheel times the radius squared. What's the mass of the wheel? Well, I'm not going to take apart my desk chair to find that, so by searching on Google, we can find this one on Amazon is 16 ounces, or 1 pound, or 0.4536 kilos. So by substituting that in, we get that the moment of inertia of one wheel is 0.000164 kilogram meter squared, which is one of my least favorite units. But since there are 16 wheels, we can multiply that by 16 to get 0.00023424. Alright. Plugging that in for a new equation gives us that the friction force is negative 0.155 newtons. God, I hope I did that right. Okay, so now that we finally have our friction force, we can relate it to the law of energy conservation. So it states that our initial kinetic energy plus our initial potential energy equals our final kinetic energy plus our final potential energy. Since the aren't moving up or down, we don't have potential energy. Instead, we have the work done by friction. So kinetic energy is equal to 1/2 the mass times velocity squared, and the work done by friction is equal to the friction force over a distance. The distance we're talking about is the total distance in which friction takes part in, or the entire distance of a runway here. But I have a trick. Notice how the glass panels act as a measuring device since they're all the same length? Well, all we have to do is measure the length of one of these glass panels, and we're set. In this shot here, it looks like the glass panel is twice the length of this desk, plus a bit of extra for the divider. The divider looks a bit tricky. I was unfortunately able to find something in real life that fit the description, so we'll have to be smarter than that. Comparing the width of the chair to the divider, it looks like around 1.5 times larger than the back of the chair. The back of my chair is around 1.5 inches thick, so I'll make that 2 inches, or 5.08 centimeters. Adding the length of the desk, that brings our total to 104.04 centimeters, doubling to 208.08 centimeters, or 2.0808 meters. Lastly, it appears that the car travels around 9.5 of these windows, so that brings the total distance around to around 40.5756 meters. Multiplying that by our friction force brings us to negative 6.286 joules. Finally, we are able to solve the equation by considering the initial kinetic energy and work done by friction, bringing our total to, drumroll please, 2.48 kilograms. Wow, that's it? That's a lot lighter than I thought it would be. I mean, it checks out. A real car would be a lot too heavy to actually do the things that it does in the game, like rocket across the stage at the speed of sound. Thank you for watching, and I will see you next time when I finish with the Epic Mickey 2 TAS version 2.